Hello everyone, welcome to 1045 Engineering. We are here with yet another video in our Grind 75, a Better Blind 75 coding series. So today's problem is on finding the minimum height trees. It's a very common problem, MHTs. So let's quickly jump into the problem statement, understand it and start solving. Okay, last time we have solved find all anagrams in a string. We can mark it checked. You can find it in the list. Let's start with minimum height trees. Okay, a tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycles is a tree. Okay. Given a tree n nodes labeled from 0 to n minus 1 and an array n minus 1 edges where edges I represents a of I, b of I indicates that there is an undirected edge between the two nodes a of I and b of I in the tree. Okay. You can choose any node of the tree as the root. When you select a node x as the root, the result tree has height h. Among all possible rooted trees, those with minimum height min h are called minimum height trees, MHTs. Return a list of MHTs root labels. You can return the answer in any order. The height of a rooted tree is the number of edges on the longest downward path between the root and the leaf. Okay. Like for example, they have given us n is equal to 4, that means there are 4 nodes and the edge is 1 0, so there is a connectivity between 1 and 0. 1 2, there is a connectivity. 1 3, there is a connectivity. And we have to find out the minimum, how can we form it in such a manner that the height of the tree is minimum. Let's say if we are considering 0 as the root, then height in this case is 1 2. If we consider 1 as the root, height in this case is only 1, right? 2 as the root, height is 2. 3 as the root, height is 2. So the minimum height is 1. Okay. Similarly, for this example, in this case, 3 is connected to 0, 1, 2, 4, and then 4 is connected to 5. So the height is 1, 2. If we take 4 as the root, the height is 1, 2. Okay. So we are given the edges, we know the total number of nodes, and somehow we have to form the minimum height trees, right? The solution is going to be a little complicated, but the approach is really simple. The idea is, let's say you have any tree, okay, let it be as large as possible, doesn't matter. What we are going to do is we are going to remove the leaf nodes one by one. So if I remove the leaf nodes, so leaf nodes are the ones that have only 1 degree, or degree in the sense would be that they are connected to only one node. Okay, they have only one edge. 0 is a leaf node, 3 is a leaf node, 2 is a leaf node. If we remove 0, 2 and 3, we'll be left with 1. That means we can pick 1 as a root and everyone else will be connected on just one level and the height of the tree would be 1. Similarly, in this case, what we try to do is we try to reach the center. Okay, let's remove the leaf nodes. We remove 0, we remove 1, we remove 2. 4 is not a leaf node, we remove 5. So in the end, 3 and 4 are left. Okay, since both of them are connected by only single edge, they both can be the root nodes for the minimum height trees. So this is one of the main things about the minimum height trees, that in the end you have to imagine it like there is a big tree, like a real tree, and you start removing all the leaves one by one, and in the end you will reach the central, that is the core root of the tree, and that will be the root because from that node every other node is at the minimum path, and that's when we will find the minimum height tree. Okay, with this we can start solving it. So there are of course few things that we have to create: the adjacency list, we have to create degree array, and then we'll start working on removing the leaves. Okay, so let's start with the solution. So what do we need first? First we need the result. So list integer result is equal to new array list. Okay, now a base case, right? Base case in this case would be when n is equal to 1. So if n is equal to 1, That means there's only one node, so we can add result dot add 0, right? And we can say return result. Let me comment this for everyone. There is only one node, so it's the root. Okay, now after this, let's create an adjacency list. So adjacency list to represent the graph. As they mentioned, tree is actually a graph with only one connected or only one connected edges and without any cycles and undirected edges. Okay, let's start with what's something is wrong with my cursor. Okay, yeah, so let's create the adjacency list. So we'll create list of set of integer. Adjacency list is equal to new array list. Okay, now we'll fill it for int I is equal to 0, I is less than n, I plus plus. Okay, so adjacency list dot add new hash set. Okay, it's a blank adjacency list as of now. Similarly, we'll create another array to store the degree for each node. So array to store degree of each node. Degree is nothing but to how many other nodes it is connected. Like 0 has a degree of 1. On the other hand, 1 has a degree of 3 since it's connected to 3 nodes. 3 has a degree of 0 and 2 has a degree of 0 as well. They are actually the leaf nodes. Okay, so int degree is equal to new int of size n. Okay, now let's build our adjacency list and the degree array. So build adjacency list and degree array. Okay, for int from edges, that is our input matrix. Int u is equal to edge 0, int v is equal to edge 1, right? As you can see from the example, we are given 2 elements in each subarray, 1 0 1 2 1 3. So 1 is at u, v is at 0, and then we form the connectivity between them. Okay, so we can say adjacency list dot get u dot add v. So we created the connection. Similarly, we'll do the same for v as well, since they are both connected to each other. Get v dot add u. Okay, after this we are going to increase the degree for each node. So degree for u plus plus and degree for v plus plus, right? Because when we added 1 and 0, we increased the degree for 1 as well as for 0. Next time we'll increase the degree for 1 and 2. Next time 1 and 3. So degree for 1 will reach 3. For 0 to 3 it will be 1. As we can see, 0 to 3 are leaf nodes, 1 is at the center. Okay, that's it. Now let's create a set to store our current leaves. Set to store current leaves. So currently all the nodes that have degree of 1 are actually the leaf nodes, right? In this case 0 to 3 will have the degree 1 and they are the leaf nodes. So let's create a set for them. Set integer leaves is equal to new hash set. Oops. Okay, now let's add initial leaves to the set. Okay, so for int I equals to 0, I is less than n, I plus plus, we are going to check for each of the degree. Wherever the degree is equal to 1, we'll add them to the list. So if degree of I is equal to 1, that means they are the leaf nodes. So let's add them to the leaf set, leaves.add I. Right, so this way, as of now, we have added 0, 2, 3 to the leaves. Okay, now we are going to iterate. Now we are going to iterate through our leaves, and with each iteration we are going to decrement the degrees such that we reach the core. So let's say once we remove 0, 3 and 2, 1 will be the only node that is left, and that can be the root. Similarly, the end case can only be that we have either one node left or two nodes left. So we'll say iterate until there are one or two nodes left. So while n is greater than 2, we'll create another set integer new leaves, which is blank, which will be blank for now. New hash set. Oops, I'm committing some mistakes today. Okay, now we'll remove our current leaf and we'll update the degree, because we want to remove all the leaf nodes one by one and reach the core, right? So we'll remove the current set of leaves and increase the degree and update the degree. That will actually be the decrement. So remove the current leaves and update the degree. Okay, so for int leaf from leaves, we'll say n minus minus, since each node will be decremented. That we have covered, out of the 4 nodes we have covered one node. I'll just simply comment this. So decrement the total number of nodes, right? That's the breaking condition for our while loop. We'll say degree of this leaf will be minus minus, so it will reach 0, and the degrees that were at 2 or 3 will decrement to 1. So when we remove 0, the degree will get decremented for 0, then for 2, 3, and then for 1 as well, right? So now we'll check for the neighbors as well, right? Because when we are at 0, we'll decrement the degree for 0 as well as its neighbor, that is 1. So 0's degree will go from 1 to 0, 1's degree will go from 3 to 2, 3's degree will go from 1 to 0, 1's degree will again go from 2 to 1, 2's degree will go from 1 to 0, and 1's degree will go from 2 to 1. Oh sorry, 1 to 0. Okay, so let's find the neighbor. neigh_pour, neighbor, adjacency list dot get leaf, right? From the adjacency list we can fetch its neighbors. So we'll reduce the degree for the neighbors, neighbor minus minus. Okay, now if at this point in time, if degree of neighbor at any point in time reaches 1, that means we have found our core node or the root node. So we'll add it to the leaves, the new set of leaves that we have created now. So new leaves dot add neighbor, right? I'll say add the new leaves, because when one's degree will reach 1 will actually become the leaf node, right? Degree 1 is actually means that we have reached the leaf node. So we had the leaf nodes for all of them. Firstly we had the leaf nodes at 0, 2 and 3, they were removed, and with each removal we are removing their neighbor's degree as well. So whenever the neighbor's degree will reach 1, we'll add it as part of our new leaves. That might be more clear with this example. So 0 gets removed, it reduces 3's degree. So 3's degree was 4. 1 gets removed, it reduced 3's degree. 2 gets removed, it's reduced 3's degree. So after 3 degrees are removed, 3's degree will reach 1. 5 is removed, it reduced 4's degree from 2 to 1. So 3 and 4 will be left in the end, in the second example. In the first example, 1 will be left. Okay. Once we have removed all these degrees, we'll say now the leaves, we'll update the leaves with the new leaves. So leaves is equal to new leaves. You can say update the set of leaves for the next iteration, like how we generally do for when we are operating with queues, right? We add the child nodes back to the queues, then again iterate over the queues. In the end, once our while loop is over, that means all the nodes that have been added to the leaves are the answers. So we can simply add them, result.add all leaves. Okay. Remaining leaves are the roots, or I can say core of minimum height trees. Okay, and simply we can say return result. Cool, let's run it. There is a compilation issue. I love when we do not get any compilation issues, but those things don't happen in the real world, right? Okay, let's run it again. It's running slow. Okay, let's submit. Great. Though I was actually expecting a better time complexity. Let's submit it again. we do this every time, right? When we get a lower time complexity. Oops, now it's much worse. Let's submit it again. You have attempted to run code too soon. Submit. Okay, 40. I don't know why the time is increasing with each iteration. The first one was at 50. That means there are solutions which are better than this one, or I would say much better than this one. This is not a very efficient solution. 28 beats 56%. Okay. If you find a better solution, please let me know. This is the only solution I could come up with. So let's understand it again. Okay. The core of the solution is to find the minimum height trees. Imagine there is a tree, right? If you remove all one by one, if you remove all the leaves, eventually you will reach the core of the tree, right? Because that would be the node that is on the smallest path from each of the leaf node. That is what we did here. Once you find the core, like in this case you can clearly see 1 is the core. So if you create the tree like this, that 1 is the root and 0 to 3 are its children, then this is the minimum height, that is 1. So in order to achieve this, now with minimum height trees there are two possibilities. Either in the end you will have only one node, or in the end you will have two nodes that will be left connected to each other. So both of them are the core. So in that case 3 and 4 both would be the solution. Like in this case we remove 5 leaf nodes, 0, 1, 2 they get removed, 4 and 3 are connected. You cannot remove only two nodes which are connected by one edge, since both of them are the leaf to each other, right? So that's why the breaking condition is the n is greater than 2. So the core of the solution is that you start chopping off the leaves to reach the core. So what we did is, first we created adjacency list to help us form the graph or the tree in this case. Second, we created an array for degree to know that how many edges each node is connected to. Now we have some nodes that were the leaf nodes. So for any node that the degree is equal to 1, they are the leaf nodes. So one by one we iterated through the leaf nodes and we reduced their degree. for the leaf nodes as well as for their neighboring nodes. Now in the process of reducing the degree of the neighboring nodes, if that node reaches the degree equal to 1, that means it is a leaf node, so we add them to new leaves as part of our next iteration, and in the end the new leaves will become a leaves, and we'll start this process all over again until in the end we have only one or two nodes left. Okay, I hope it was clear. So that's all from today's video, everyone. Yes, if you have a better solution, please let me know in the comment section, or in case if the solution was not very understandable, please let me know. I'll come up with a better solution and we can redo this. And yes, the overall time complexity will be O of n, since we'll be touching each node only once. So that's all from today's video, everyone. For anything, please let me know in the comment section. In the end, please like, share and subscribe. Thank you.